Welcome back to the Math Professors. Enjoy content that can be found in any college math class. Please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover Kirchhoff's laws today. We're really going to work with electric circuits. So there are two laws. The very first one, it says all current flowing in must flow out. So this is very similar to that network analysis example I did in a previous video, to where we said that whatever comes in has to come out. So if I have 25 going in, I got two paths coming out. So if I had 25 coming in, two paths going out, say this is X and this is 10, well, I know that that has to be equal to 15 because in has to equal out. Therefore, 25 has to equal X plus 10. So that's why X is 15. So that works essentially for these nodes here, for these junction boxes. Now, the next one says the sum of the products of I times R, which is current times resistance around a closed loop or a closed path, has to equal the total voltage of the path. So this has an extra part to it as far as that network analysis goes. That we have, we have loops here, and it's determined by these, by these squares is what they look like, but they're essentially closed loops, and I'll explain them in a second here. So here is our electric network, or our circuit. These things are our junction boxes. Now these sawtooth things are resistors, and they've labeled the resistors, R1, R2, and R3, and they've given values for the resistors for how much they resist. Now these things right here are batteries. The way batteries go is they go, from the bigger line around to the smaller line. So this particular loop right here, you can see that I have a loop right here. It's going to go from this bigger line all the way around to the smaller one. And same thing down here. It's going to go from this, this bigger electric potential to this smaller electric potential. So kind of like, dropping something. When we talk about electric potential, when you pull something up, it has potential energy. When you drop it down, it's kinetic. So electric potential kind of works very similar. So, more electric potential, less, so it's going to move around this way. So what I have is I have some loops, and I'll just draw this in color. So I have a loop going around this way, that's this loop, and bigger electric potential to smaller, so it's going to be this loop this way. So, boom. Okay. So let's start out with the nodes. So I have node 1, or junction 1, and junction 2. Now what that says, that's really for this. It says that all in must be equal to out. So, for junction box 1, what I know is that, what do I have coming in? Well, it says all current in, and current is going to be your I's. So, it's going around this way. So if I was going to kind of draw this, it's going this way, and, it's going this way. Similar when this thing is moving around this way, you can see it's going to go, I don't think I have that right. It's going to go this way, there we go, and therefore this is going to go this way and around this way. So just to make sure that I get some arrows here, it'll be a little easier to look at my ins and outs, and those are really just coming from those loops. All right, so let's take a look at junction box 1. Well, what's coming in is going to both be I1 is coming in, and also I3 is coming in. So I know that. Let's do this so it's easier to see. So I have I1 plus I3 has to equal the current coming out, so coming out this way is going to be I2. Now I have another junction box over here. Sometimes you'll get the same exact equation, and we'll see if that's the case. So going in is going to be I2, and then coming out is going to be I1 plus I3. And what we notice is those two equations are equivalent. So I don't really need the second equation, so let's just use the first. Now, the other one says that the sum of the products of current times resistance around a closed loop is equal to the total voltage. So now we have to go after the loops. So let's call this, loop 1, and let's call this loop 2. So loop 1. What I know is the sum of I times R, so I'll write it over here. The sum of I times R has to equal that voltage. or really the total voltage, but we can see there's only going to be one voltage on the loop. So let's do loop 1. So loop 1 is here. I have I times R plus, remember going around this way, this also I times R. So I have I1 R1 plus, going around this way, I2 R2 has to equal its voltage, which is going to be that battery on that particular loop. So that battery is going to be equal to 3. Now I have the second loop over here. So second loop, very similar. The sum of I times R has to equal V. So the second loop is going, this way. So I have I2 R2 plus I3 R3. I2 R2 plus I3 R3 has to equal this thing's electric potential, and that voltage is going to be 4. All right. Now remember that I know the values of these resistors, so I'm going to rewrite these equations. So these two equations here are going to be R1 is 4, so this is 4I1 plus R2 is going to be 3, so 3I2 is equal to 3. And then very similar, I know R2 and R3, so R2 is going to be 3I2 plus R3 is 1, so 1I3 is equal to that voltage, which is 4. Okay, so what I have is I have some systems of equations here, and let's go ahead and write these things, your I1s, your I2s, your I3s, and then your equals, which are going to be your voltages. So let's rewrite this one. Remember that this one's equivalent, so I don't really need that one. So I can say I1 minus I2 plus I3 is equal to 0. All right, so now I have, 3 equations, 3 variables. So I have I1 minus I2 plus I3 is equal to 0. This one says 4I1 plus 3I2 plus 0I3 is equal to 3. And then the last equation is just 3I2 plus 1I3 is equal to 4. And I can set this up as a equivalent matrix to where the first column are the coefficients of I1, so 1, 4, 0. This will be I2, so negative 1, 3, 3. And then finally I'm going to have 1, 0, 1. And this is going to be equal to 0, and then 3, and then 4. Now we spent a lot of time row reducing these matrices by hand. Usually when we get to an application section in a class, I'm saying, well, it's fine. You're welcome to just use your calculator. So that's what I'll do. We're going to plug these things in and kind of walk you through it. If I want to row reduce this matrix, you hit the second button and you can see that matrix button, which is the 4th button down, matrix, and you can see names, math, and edit. So I want to edit a matrix. I want to put that in there. Notice this is a 3 by 4. So when you hit edit, this has to say 3 times 4, enter. Then we just type them in. Now, when you write it, you write it, horizontally. So 1, negative 1, 1, enter. So every time you hit a number, you have to enter. So 4, enter, 3, enter, 0, enter, 3, enter. The last row, 0, enter, 3, enter, 1, enter, 4, enter. Okay. And I know I plugged it in the calculator, but I always like to double check. I entered it horizontally, so I'm just going to check it vertically. So the last row is, the last column is 0, 3, 4, 1, 0, 1, negative 1, 3, 3, and then 1, 4, 0. Fantastic. So now you have to quit out of here. You got to take it to your home page. So second quit button, second, this second button over. And now you can work in here. So I need to row reduce echelon form this. So, I'm going to call this matrix A. So in my calculator, I'm going to go RREF, and I'm going to do matrix A. And then this is going to give you the row reduce form of that. So back to matrix. So second, that 4th button down, and I have to do math on it. And way down here is RREF. Boom, reduce echelon form. Then I go second matrix, say label A, because that's what I put in there. Now this is going to have in your calculator, it's going to have this. A, and then close parentheses. So enter, we get 1, 0, 0, 0, and then 0, 1, 0, 1, and then 0, 0, 1, 1. And let's see what that says. Well, it's kind of interesting because what does that say about 1? So Remember, this says I1. You know, the stop says I1 is simply equal to 0. That's kind of interesting. I2 is equal to 1. And then I3 is also equal to 1. So that's, what a boring answer. But it is what it is. And on the next example, maybe we'll do 3 loops to get something a little more interesting than this. But that's what it was asking us to find, is find I1, I2, I3. Let's just make sure that makes sense. So, does this work out? I1 minus I2 plus I3 equals 0. All right, so 0 plus 1, 0 minus 1 plus 1 indeed is 0. 4 times 0 plus 3 times 1 equals 3. Sure does. 3 times 1 plus 1 times I3 is 1 is equal to 4. Yeah, it sure does. That sure does work. Okay, so these are our answers for our currents. So if you like the content, please subscribe.